Okay, so this is the video notes for 7.4, which is solving with roots and inverses. You are going to want your graphing calculator out for this because some of these equations that we're going to solve, you're going to want to do the roots in your calculator, and I will tell you how to do that. And you're also supposed to be doing this on notebook paper. Okay, so prepare yourself. You can pause the video until you're ready. And if I go too fast on a problem, please pause the video, catch up, and kind of do this at your own pace. So the objective of this lesson is I can solve with nth roots and radicals, and I can find and verify inverse functions. So we are finally solving using the nth roots that we've been practicing, and then we're also going to find inverses just in general, but then also, with nth roots. Okay, solving with nth roots. So there's a general process, and honestly, we use this with pretty much every equation that we solve, but with nth roots, this is the easiest way I think about it. So the first step is to isolate the exponent. So whatever is being exponented or whatever is being taken to a power, you want to isolate that first. Then you want to use the inverse operation to undo the exponent. So sometimes you have to figure out, okay, this is what's happening to x, here's how I undo it, and that can be a process that you practice. And then lastly, you need to finish getting the variable alone. Remember too, when you are inserting a even root into a problem yourself, so you are physically writing in square root of both sides, or fourth root of both sides, or sixth root of both sides, you do need to account for the fact that there can be a positive or a negative version of that answer. And so when we see that throughout this, I will mention that as well. So on example A, what I want to focus on is the fact that the only thing being taken to the fifth power is the x. The 4 is not being taken to the fifth power at all, so we need to isolate x to the fifth before we do anything else. So I'm going to start by dividing both sides by 4. If my pen cooperates, there we go. So I get that x to the fifth is equal to, and then in your calculator, you can simplify the right side, 32. Now that we have isolated the exponent, we need to use the inverse operation, and it's something to the fifth power. So remember, we are using powers and roots to undo each other. So I will need to do the fifth root to both sides. This is an odd root, so I don't have to worry about plus or minus. X equals, and then I can do the fifth root of 32 using the table. You can also do higher order roots. Let me remember how to do it. If you go to math, you can go down. So on your calculator, hit math, go down where it has a root that has a little x in it, and then you can replace whatever the index is with 5. So you can do fifth root of 32. I got out 2. Again, some of those you will have memorized, but then there might be also questions where it doesn't simplify nicely and you would want to get a decimal answer. So knowing how to do that in your calculator is great. Also, when you hit math, you can see cube root, at least on my calculator, is pre-programmed in, but any root over 3, you are going to have to type in the index specifically. Okay, on example B, I have, x minus 3 being taken to the fourth power. So x minus 3 is what is going to that power. So we need to isolate the exponent, which is already done. Everything on the left is being taken to the fourth power, so I can do the fourth root on both sides to undo that. This is an even root, so remember, when we take an even root, we're going to be left with x minus 3 on the left and then plus or minus the fourth root of 21. Just like you would solve with a square root, having to go through and write plus or minus, you need to do that on any even roots, and I'm making sure that index looks like an index. Remember, try to be careful with those. Then we need to get x alone, so I can add 3 to both sides. And because only the fourth root of 21 is being plus or minus, when I write this, it's going to kind of be like quadratics. The 3 will go in front, then I can have plus or minus fourth root of 21. Now that is technically the most simplified answer. If you were not putting it as decimals, you would leave it there. And then you can also go through and find the decimal approximation, which since 4th root of 21 doesn't have anything nice, I'm gonna go through in my calculator and do 3 plus. Again, you hit math. You go down to the xth root where you can put in an index of 4. I can then put 21 under the radical, and I get one of them, I'll just round to the nearest hundredth, is 5.14. And then I can do the subtraction version. So 3 minus math down to the xth root, 4th root of 21, gets me 0.86. So again, with even roots, you can have multiple solutions. You can also think about how something to the 4th power would interact with the x-axis. It could cross through it a maximum of 4 times. And this one, it's going through it twice, and then probably has, I don't know, complex solutions or something for the rest. Or you could have multiplicity on both of those roots. Okay, number 6. So on number 6, we have x plus 5 to the 6th. So I don't need to isolate that anymore. I can do the 6th root on both sides. Again, this is an even root. Make a special note, when you have an even root, you are putting the even root into the problem. So you need to do plus or minus. And then we can try to simplify the 6th root of 729. Again, if you have that little table, that's also going to be helpful for you. Oh, it gives me 3. So x plus 5 equals plus or minus 3. Again, use your calculator on this. Then we can subtract 5 from both sides to get x alone. So x equals -5 plus or minus 3. And then go through and find the actual 2 values. So -5 plus 3 would be -2. -5 minus 3 would be -8. Guess I can box them. I use the little clouds for decimals, or at least today that's what I'm doing. Now on the last one on this page, we have 1/2 x to the 5th. Remember, the x is the only thing to the 5th power. If we had parentheses around 1/2 and x, both of them would be to the 5th power, but since those parentheses are not there, then x is the only thing to the 5th power. So I need to get rid of that 1/2. I like to do that by just multiplying by the reciprocal or by 2, but 2 over 1 technically will get rid of that. So x to the 5th equals, then I can take 512, multiply it by 2, I get 1024. This is an odd root, so you do not need to worry about the plus or minus. Then I can do the 5th root on both sides to undo something to the 5th power, x equals. And then again, you can use that little table to help you, or hit math on your calculator, go down to the xth root, put in 5 of 1024, and I get 4 out. So that is that page. So that was solving problems where x was taken to a power. We can also deal with situations more like this, where x is under a radical, and these get kind of fun. So the process for solving radical equations, and again, we could really have any nth root, so you could even have 4th root, 5th root, 6th root. This just has a square root and a cube root on it, because I want to show you some things with these two operations. But it's a very similar process. You isolate kind of the complicated thing, which in this example would be the radical. So whatever type of root you have, that's what you're going to isolate. You then want to use the inverse operation to undo that radical. So like in the previous page, how we were taking something to the 5th power and 5th rooting it, now we are dealing with the 5th root and we want to 5th power it. And then you want to get that variable alone. Okay, we are not inserting the radicals into these problems. The radical is written there, so you do not need to worry about the plus or minus on even roots. When you are writing in the radical, that is where you need to worry about that. Otherwise, it's the implied positive root. So on the first one, I need to get the actual root alone, which is the square root of 3x plus 37. So I'm going to start by subtracting 19 from both sides. So I get the square root of 3x plus 37 equals, and then I have 27 minus 19, which is 8. Then to get the x more isolated, I have to get rid of the square root, and I can do that by squaring both sides. So that will leave me with 3x plus 37 equals 8 squared, 64. Then I can subtract 37 from both sides. So 3x equals 64 minus 37, 27. And I can divide by 3 on both sides. X equals 9. These are also good questions to go back and check in your calculator just to make sure that you are getting the left side and the right side equal. There would be the kind of rare situation where a domain restriction would keep one of these solutions being valid from being valid, so it's something you want to be aware of. The same thing, I guess, could happen on this page as well. If you had a domain restriction because of one of your roots, then that's something you would want to be aware of. But I guess on the previous page, since they're all 2 powers originally, there wouldn't be domain restrictions. On this page, there would be domain restrictions because a square root comes with a domain restriction. So at the end, you'd want to go through and just take that 9 and plug it in here in your calculator. So I would do the square root of 3 times 9 plus 37, and then outside of the radical, so you have to hit the right button, I can write plus 19. I get 27 equals 27, so I know I'm good and it's not extraneous. So same process on the next one. The only thing under the radical is the 12x, so I need to start by moving the 13 to the other side with addition. So the third root of 12x equals 6. Then I'm going to go through and cube both sides because that will undo the cube root. So 12x equals 6 to the third, 216. And then I can divide both sides by 12 to get x alone. So x equals 18. Again, you want to plug that in to make sure it's not extraneous. So you want to do the third root. Again, you hit math. Third root of 12 times 18 under the radical, arrow to the right, so that minus 13 is not under the radical, and you should get out -7, which is what I did. So if you do not get out -7 on that one to make sure that it is in fact equal to -7, then you are typing it wrong in the calculator, and I want you to figure that out before you move on. Okay, next page. So there are a few other situations where you can see a radical that you are solving, and sometimes you have an equation that will actually have 2 radicals in it. So if you look at example G and H, those are 2 situations where there are multiple radicals in the question. The idea there is to get a radical equal to a radical, or a cube root equal to a cube root. Because once you have it kind of balanced in that way, where there's a single radical on either side, you can do the inverse operation to both of them at the same time, and then you're making your whole life easier. So if you look at example G, right now it's like, oh my gosh, I have a lot of radicals. What the heck do I do? But since we have just the square root on the left and just the square root on the right, I can actually square both of them to start, and then I get a much easier problem in the next line. Because if I square root the left and the right side that are both only square rooted, we are left with what was under the radical. Then I can solve that. So I'm going to subtract x from both sides. I get 3x plus 1 equals 10. Subtract 1 from both sides. 3x equals 9. Divide both sides by 3. X equals 3. And again, you do have to check these for extraneous solutions. So I'm going to take that x value. I'm going to plug it in here on the left side using my calculator. So 4 times 3 plus 1, I get 3.6 and some change. But then I'm going to compare that to what I get when I plug it in the right side. The square root of 3 plus 10, which is also the same value. And I can tell they're actually exactly the same based off my calculator because the other one is stored there. So they're the same, we're good to go, and that is a solution that I can keep. On the next one, you can tell that I do not have a radical on either side, but one thing I can do with the very beginning is actually add that second radical to the other side. And what's nice about that is then you have a cube root on both sides, and if you cube root both sides, you can make it a lot easier. So the cube root of 12x minus 5 equals the cube root of 8x plus 15. Now, there might be some people that are like, oh, well, why don't we just cube root the original problem? But remember, if you're cube rooting these two things, that means you have those two things times those two things, or sorry, if you cube the entire problem, you have those two radicals times those two radicals times those two radicals, and you'd have to FOIL it out. So it's not just as neat cubing it from the beginning. You really need to get things on both sides of the equation so that when you're cubing it, you're not having to do a bunch of FOILing. Then we're good to cube both sides because both radicals are isolated. So I'd end up with 12x minus 5 equals 8x plus 15. Then I can move all my variables on one side. So 4x minus 5 equals 15. I did that by subtracting 8x from both sides. I can add 5 to both sides to get that 4x equals 20 and divide both sides by 4 to get that x equals 5. Again, you do want to plug that in. You can plug that into the original equation and make sure that you get 0 out. Or if you did that first step correctly, you could plug into both sides of that green equation to make sure you get out the same thing as well, which I will now do. So again, you hit math. You can use the cube root button if you want. 12 times 5 minus 5. Go out of the radical. Subtract, I'm just doing the original problem in my calculator. Third root of 8 times 5 plus 15, and that was equal to 0, which it should have been. So since 0 equals 0, that is not an extraneous solution, and that solution can stay. Okay. Now, the next ones, we do not have radicals on both sides. We have a radical on one side, it is isolated, and then the other side is a non-radical. So we're actually going to start in a similar way, and that we have to go through and say, all right, well, this is an isolated radical. I can square both sides to undo the square root, but you have to remember what happens when you square the right side of that equation. You have to FOIL it, okay? It is not under a radical. So when we square that binomial, it's x minus 2 times x minus 2. So I'm going to write this out as 6 minus 5x equals x minus 2 times x minus 2. First, outside, inside, last it. So 6 minus 5x equals x squared minus 2x plus 4. Now that is a quadratic that I need to solve. So my suggestion would be to set the whole thing equal to 0 by moving everything to the right and combining your like terms, and then you can factor it to solve. So if I have 0 on the left, that means, okay, x squared is not going to change, but I have negative 4x plus 5x, so plus 1x, and then I have 4 minus 6, so negative 2. Then you would go through and guess and check it. So x and x, two numbers that multiply to negative 2 and add up to 1, so positive 2, negative 1. And that would give me a solution of x equals negative 2 and x equals 1. Now, this part's not particularly fun, but it is really necessary. You do have to go through and take each of those x values and plug them into both sides of the equation. So I'm going to start by plugging negative 2 into both sides, make sure that they equal the same thing. So I have the square root of 6 minus 5 times negative 2. I got 4. And then I'm going to do it on the right side. Negative 2 minus 2. Ooh, that gives me negative 4. Okay, 4 is not equal to negative 4. And I did plug it in correctly. The reason that that happened was it was an extraneous solution. Then I need to do the same thing with 1. So the square root of 6 minus 5 times 1 equals 1. That is equal to. Then I have 1 minus 2, negative 1. Oh man, once again, that is an extraneous solution. So this one actually has no solutions. Another cool way to check that one is you could put this into Desmos and this into Desmos and see if they intersect. and they're not going to intersect anywhere, which is another reason there's no solution. Okay, so same process on the next one. We're going to go through. I have a radical on one side and a non-radical on the other side, but I can square both sides. So I get 4x plus 17 equals, FOIL this out, 4x plus 17 equals x squared minus 1x plus 1. Now it's a quadratic, so I need to set everything equal to 0 and move it all to the right. So x squared doesn't change. I have negative 1x, and I'm also subtracting 4x from that, so negative 6x. And then I have 1 minus 17, or negative 16. Again, solve that quadratic. I would do that by factoring. Guess and check, x and x. I need two numbers that multiply to negative 16 and add up to negative 6, so negative 8 and positive 2, which would give me solutions of positive 8 and negative 2, and then those are what we would check in the calculator. So again, you go back to the first line, and you're going to plug in those x values on each side, making sure that the left and the right side actually do give you the same values. So if I plug in 8, I'm going to have the square root of 4 times 8 plus 17. I get 7 equals, and then I have 8 minus 1, so 7. Cool, that answer works. The next one I can plug in negative 2, so square root of 4 times negative 2 plus 17. 3 equals, go through again. I have negative 2 minus 1, that gets me negative 3. Well, those are not equal, so that second solution is extraneous. You see how important that check is? I know it's a pain, but you do have to verify that those are the actual solutions that we want. Okay, so we're gonna do one more solving, and then we're gonna start talking about inverses. And when we solve, there is a more challenging situation that is this one. So this could be like extra credit. I could give you one of these occasionally, but it is not something that we really have to have mastered this year. They're for sure going to make you get better at this next year. But this is how you would solve a problem when you have a radical on both sides, but one of the radicals is not covering the entire left side of the equation. It's only part of it. So we go back to this idea of isolating a radical, and as soon as you have one of the radicals isolated, you can square root both sides. So that's where I would start on this one. I would square both sides. So I'm going to square the right side. That will get rid of that radical. We will be left with x plus 8. I'll write it over here though, and you'll see why. But on the left side, since I have one radical and then something that's not in a radical, it doesn't simplify as nicely. So I'm just going to write out, okay, square root of x plus 1 times square root of x plus 1, which is what happens when you square that. And then we'd have to FOIL out the left side to simplify it. Okay, so this is a bit of work. Remember though, if you have the square root of something times the square root of that something, it actually simplifies very nicely. So the square root of x times the square root of x gives me just x. The square root of x times positive 1 is plus 1 root x. I have that on the inside as well. And then the last two terms are 1 times 1, so 1, and that equals x plus 8. Now is where a lot of people get very nervous. It seems confusing, but here's the clue. You need to re-isolate the other radical. Once you've gotten rid of one radical, which we were allowed to do because it was isolated, we then need to re-isolate the other radical and then get rid of it. So we can do that by combining like terms on the left. I have x plus 2 square root x plus 1 equals x plus 8. Again, those were like terms. We had two of them, so I wrote it that way. Then we can actually move the x and the 1 to the other side. So I'm left with 2 square root of x equals, this actually simplifies really nice. X minus x is 0. 8 minus 1 is 7. Then we can divide both sides by 2. to get the square root of x equals 7/2. Ah, see how we did that? Kind of crazy. That's why it's a challenge question. And then we're going to square both sides. And remember, this is so funny. You'd get through the entire problem, and then a lot of people would write 49/2. It's 49/4. You have to square the top and the bottom. So 7 squared over 2 squared. Then you would want to plug that solution into the calculator, which is a little crazy, but you can do it. So the square root of fraction 49/4 plus 1. I got out 9/2. And then we got to see what that's equal to. So square root of fraction bar. Learning a lot with our calculator and how to plug things in. Oh my gosh, I also got 9/2, so we can keep that solution. Woohoo! So again, that is sort of the hardest solving one that you might see this year. Next year, you're going to spend a lot of time solving with nth roots and radicals and all of that fun stuff. But now we are actually going to go the other direction, which is back to inverses and talking about how to find inverses. Now, it has been a second since we've talked about inverses and finding inverses. So I did write out that process again. The general process for finding the inverse of a function is you take the function, you rewrite it in terms of x and y, you swap x and y, and then you rearrange the equation so that your new y is alone. And I know it sounds easier than it is in application, so we can practice that process so that you can find the inverses of this. And then technically, if you graph the inverse and it is a function, you should put your final answer in function notation. I think on most of these, they are going to still end up being functions, so you will use like f to the negative first to say that you have an inverse. So let's practice the first one. So I have f of x equals 2x to the third plus 1. So I'm going to start by rewriting it in xy notation. It's because you do not want to be swapping x and f of x. That gets out of hand very quickly. Then we are going to take x and y and put them in each other's spots, because when we have an inverse, the x and y are flipping. It's y. Inverses are always a reflection in the line y equals x, because that is where x and y kind of swap with each other. Then we have to go through the process of isolating y again, and that just means solving for y. The problem is the stuff on the other side of the equal sign is not going to combine to give you a whole number. You're just going to get y alone. So I'm going to subtract 1 from both sides. At this point, I usually write y on the left, and then I would have x minus 1. So we're just moving everything away from y one step at a time and then writing it on the other side of the equation. Now remember, 2 is not being cubed. Y is being cubed. So I'm going to start by getting rid of the 2. And you're just going to leave this as a fraction like that. So y to the third equals x minus 1 over 2. It's not pretty, but there we are. And then we can, cube root, not square root, cube root both sides. Y equals the cube root of x minus 1 all over 2. If you wanted to be extra special, you could go through and rationalize that denominator. Technically, that is a radical in the denominator. But with inverses, we are just looking for a function that undoes the other function. And so if you just have it like that, I would accept it. Remember I like to say bonus points, but this is something you should get into the habit of. Since this is a cube root function, it would be a function. Cube roots, when graphed, are functions. There are no domain restrictions on this one. So we can write f inverse is, and then it's the third root of x minus 1 all over 2. Now, the next one is going to freak people out. I know it's going to freak you out. You're going to be okay. The reason it'll freak you out is because x is in the denominator, so let's talk through it. First, we're going to replace f of x with y. So y equals, and then I'm going to put that negative up top. When there's a negative in front of the fraction, it can either go to the numerator or the denominator, but only one. So I normally put it in the numerator so that I don't have to worry about dealing with it in front. Now, we need to we need to swap x and y, my bad. Whoops. There we go. So x equals negative 2 over 5y. Now we need to get y alone. And here's the thing. Y is in the denominator, which freaks people out. But But if you can go ahead and multiply by that denominator, that's going to get y out of the denominator, and then you can go from there. So my suggestion is multiply by 5y on both sides. 5y times x equals -2. Now y is not in the denominator, so I can deal with it a little better. You also, on the previous step, could have written x over 1 and cross multiplied. You would get the exact same thing. Then I need to get y alone. It's being multiplied by 5 and x, so I can divide by 5 and x to get y alone. So y would be -2 fifths, and then you could have, let's see, x would be in the denominator, so -2 over 5x. What's crazy about that one is it is its own inverse. Whoa! And there is a domain restriction on that. So f inverse of x equals -2 over 5x. The domain restriction is that x cannot be 0, because that would make your denominator go to 0, which is not allowed. Now, I know you're like, how can something be at the inverse of itself? Well, all that means is that that original graph has symmetry on the line y equals x. So let's see. This graph probably looks something like this. So what happens with that graph is, even if it is reflected over the line y equals x, the graph actually is the same because it would have had that symmetry to start. Maybe it would look like this. You can put it into your calculator to check it as well. Honestly, just because there's a negative, I think it would look like this. But regardless, since that symmetry was there to start, and it's the same and has that symmetry in the line y equals x, you can have rationals that are their own inverses, which is kind of cool. Okay, and then the last thing we're talking about is verifying inverses. So sometimes I'll say, hey, you find the inverse, but then other times I will say verify that this is the inverse of some function. And for this, we are really going to be using those rational exponent properties. So when we have a fractional exponent and you have to go through and evaluate or simplify, that is when this comes into play. So the process for verifying an inverse is you find the function composition going both directions. Now, function composition freaked you guys out the first time, so it's probably going to freak you out this time, but that's why we bring it back, so that you see it twice. And then if both of them simplify to x, they are inverse functions. So here's the idea. You're going to take this going both directions. You're going to do f of g of x, and it should equal x if they're inverses. And then you're going to do g of f of x, and again, it should simplify to x if they're inverses. So if we do that going both directions, and they both simplify to x, they are in fact inverses, and that is how you prove it. Okay, now I know you're like, I don't remember how to do that. So let's walk through that process. So when we do f of g of x, you want to take the g function and you want to replace x in the f function with the g function. And I like to do this with parentheses. So f of g of x, you can also do fog of x. That's a different way of writing f of g of x. I'm going to have 1/4 in front. Then I'm going to take whatever x is and take it to the third. I like to write kind of the outside of the f function, leave parentheses there, and then I can just plug in whatever the g function is into that. So inside, I'm going to put 4x to the 1/3. Now I need to simplify that, which is why we have been practicing fractional exponents and their operations, because that's kind of awkward to simplify. So here's what I notice. I want a different color. There we go. Here's what I notice. I have something to the 1/3 power, and then I take that to the 3rd power. That is like having 4x that is being cube rooted, and then I'm cubing it. Okay? So you can prove that to yourself by doing this. You can say, okay, so 4x is to the 1/3 times 3. So I have 1/4 times 4x to the 1/3 times 3, which is to the first, which is just 1/4 times 4x. Well then, if you have a fourth of 4x, that is just a single x, and it reduced all the way down to x, which is what we wanted. But again, you gotta know your properties and what's mathematically valid and what's not mathematically valid, which is what makes that difficult. Then we go the other direction. So then I take the g function, and we'll practice this more when I'm back, don't worry. I know you're probably like, oh my gosh, that's so weird. Okay, so now we're gonna do it the other way. The g function is, and let me write out, g of f of x equals, parentheses, 4 times whatever we're plugging in, all to the 1/3 power. Okay, so you gotta pay attention to your parentheses. That is our g function, at least the outside of it. And then we're plugging in 1/4 x to the 3rd. Now, pay attention to the order of parentheses. What this is telling me is you are gonna take it to the 1/3 power at the very, very, very end. So we need to simplify the inside stuff first and then take it to the 1/3 power. Well, if I simplify the inside stuff, what I end up with is, and let me change colors again. I have 4 times a 4th of x to the 3rd. Well, 4 times a 4th of x to the 3rd would just be 1 x to the 3rd. All to the 1/3 power. Well, 1 x to the 3rd is just x to the 3rd, all to the 1/3 power. X to the 3rd to the 1/3 power is x to the 3 times 1/3, which is x to the 1st, or x. Ta-da! So since I did the composition going both ways and they both reduced to x, I know that f of x, and my pen goes off. I know that f of x and g of x are inverses. And that's that process. Okay, so make sure you have gone through that problem. You guys can practice that on Delta Math and make sure you feel good about that. And then we will do some extra examples when I'm back to make sure you guys feel good about that. Thank you. Please be good for the sub.